It's possible to use calculus to develop lots of rules for volume. This is just one example. We're going to actually develop the rule that the volume of a sphere is 4/3 pi r cubed. So once again, we're maybe very difficult, but that is a two-dimensional circle, and imagine that being a sphere. So it's got a radius of capital R, and this will be my y-axis and my x-axis. Now once again, we're going to take a very, very small, thin sliver out of the sphere, and we'll let that have a radius of r. So if I just look at that, this will be, because that's on the y-axis, this will be dy, small increase in y, and this has a radius of little r. And so my volume, which I'll call dV, is approximately equal to, and once again that slither is going to be very much like a cylinder with vertical sides if we take it very, very thinly. So dV is approximately equal to pi, the radius of that slither is r squared, times dy. Okay, now what I want to do is add up all those slithers. So take slithers everywhere right through, horizontal slithers, and add them all up. The way to add them is to integrate. So the integral of dV is equal to V, and that'll be the integral. If we integrate that side, we can integrate this side. So that'll be pi r squared dy. Now, we've got to set some bounds here for this integral. If this has got, this sphere has a radius of r, then this will be minus r down here, and this will be plus r on the y-axis up there. So my bounds are going to be between minus r and plus r. We're going to integrate with respect to y, but r is going to change. Out here, if I took a slither right through the middle there, little r will be equal to capital R. And it's approaching 0 as the slithers get closer to the top or closer to the bottom. So we've got to find some way of coming up and replacing this r with something in terms of y. So if I had another side look here, there's my x and y. So here's my radius r, and this is y units above. So if I've travelled y units above the origin here, here's my slither, it'll be right all the way through, but at a radius of r. And we know that that's going to be capital R, the radius of the sphere. So using Pythagoras, we've got r squared equals y squared plus r squared. We want to do a substitution for little r, so we can make it the subject here. So we've got r squared equals, bring the y squared over, and you get r squared minus y squared. R is going to be a constant for a given sphere. So we've now been able to develop an integral that just has y's in it plus a constant, and r squared, which is also a constant. So my volume is equal to the integral from minus r to plus r of pi. R squared is equal to r squared minus y squared dy. Okay, and that'll be equal to, the pi will come out the front, minus r to plus r of r squared minus y squared dy equals pi. We can now do the integral. R squared is just a constant, so that'll be r squared y minus integral of y squared, add a power on the power, y cubed on 3 between minus r and plus r. We can now do a substitution in pi. Now we let y equals capital R, so that'll be r cubed when I multiply r squared times r minus r cubed on 3. So that's when I substitute in capital R, minus when I substitute in minus r, so that'll be negative r times r squared, so that'll be negative r cubed. And I substitute in negative r there, it'll be minus negative r cubed on 3. Once again, really important with negative signs here. We've got substituting in the first bound up here, positive r, we get that, and then minus, and then we've got to actually substitute in negative r here, and so negative r times r squared is negative r cubed. Minus comes down, and then when we substitute negative r in for y cubed, we get negative r cubed. Okay, so we get pi r cubed minus minus r cubed on 3 would be just equal to 2r cubed on 3. Minus becomes a plus r cubed. And then a minus becomes a plus, but then it goes back to a minus again, r cubed on 3. Equals pi. If we take r cubed on 3 from r cubed, we get 2r cubed on 3. And 2r cubed plus 2r cubed is 4r cubed on 3. So 4r cubed on 3. And we're asked to express it a little bit better than that. Put the 4 on 3 at the front, pi r cubed, which is what we're asked to do. So the concept is that integration is used for adding up slithers. If you like, these very thin circles that could resemble very close, if you make these slithers very thin, that they will look like cylinders. And the volume of each of those cylinders is pi r squared dy, if dy is the height. To add up all these slithers, we actually use integration, and we're doing it along the y-axis. We need to replace that r squared with something in terms of y, and we use Pythagoras here. We've got a right angled triangle. We know that r squared is equal to y squared plus r squared, so we can make r squared the subject, and then that allows us to do the substitution in for that r squared up there. The bounds, on the y-axis we're going from negative r, there's the origin, up to positive r, and when we do the integration, the pi, the constant, can come out the front. We've got to be really careful with negatives, going from negative r to positive r, and we end up with collecting all the like terms and getting the answer that we're asked to find.